guys, in this video we're going to take a look at a very intuitive algorithmic approach called the binary search algorithm. It's basically a quick way of searching through a sorted list, and it's highly efficient, way more efficient than a brute force linear search. So let's take a look at it at one example with this list that we have here. So this bolded part, the 2, 8, 9, so on and so forth, that represents our sorted list, and we've just labeled all of these elements with their indices from 0 all the way to 35. So we have 36 elements here. So let's say I want to find the index of 68. Well, 68 happens to be right here. That's at index 22. So if we do the traditional linear search, we're going to start at 0, and then we'll say, is it 2? No, it's not. So we'll go to 8. Is it 8? No, it's not. We'll go to 9. It's not 9, so we'll go to 11. And we'll keep jumping like that. And we'll keep going all the way until we get to 68. And that's going to take 22 or 23 steps until we get to that 68. Now that may not seem bad at first, but suppose now we have 1 million or 1 billion elements in our sorted list. And we want a quick way of finding a certain element that happens to be near the end of the list. Well, it's going to be pretty hard to find the element if we start from the beginning and linearly search through the list. So there has to be a better way of doing this. Well, that's where the binary search comes in. So with the binary search, essentially what we're doing is we're taking two bounds called our lower bound and upper bound. So if this represents our lower bound and this represents our upper bound, we're basically finding the middle of that. That's going to be around here. And we're checking whether that's our element. So we ask the code, is the middle element the one that we want? And if it's the element that we want, then we're all done. If it's less than the element that we want, we set our upper bound to the middle. So our new upper bound is that old middle element. The lower bound stays the same. And then we again ask ourselves, is the new middle the element that we want? And we keep going like that. But if the element is greater than the middle value, then instead we move the lower bound to where the middle was before. And we keep the upper bound where it was. And then we ask, is this new middle the value that we want? And so we keep doing that. So maybe the value might fall within this range. And then maybe it might fall within this range. And eventually we're going to end up with a single value that we're checking. And at that point, if that value is what we want, then we're all done. We can return the index of that value. If it's not the value that we want, then there's no point in continuing the search any farther because the lower bound is going to be greater than the upper bound at some point. And that's when we know that the element is no longer in the list. So let's try this out with the list that we have here. So our lower bound is going to be at the 0th index, and our upper bound is going to be at the end. So we can just say that it's going to be at 36. For simplicity, we'll keep it one greater than the last index. So this is going to be our upper bound. And so where is our middle element? Well, that's going to be at 0 plus 36 divided by 2. So the middle is going to be at index 18. So here's our middle. And so we ask ourselves, is 58 the element we want? Well, 58 is not the element that we want. So is 68 greater than 58 or is it less than 58? Well, 68 is greater than 58. So we're going to adjust our lower bound. So now our lower bound is going to appear here. And we no longer check any of these elements in this left half. So now we start again. Our lower bound is at index 18 and our upper bound is at index 36. And so we find the middle index. That's going to be 18 plus 36 is 54 divided by 2 is 27. So that's going to be this element right here. And this is going to be our middle element. So at index 27, we have the element 77. Is that the element that we want? No, it's not. But 68 is less than 77. So it's going to appear in this left half. So again, we can rule out this right half here, and we can adjust our upper bound so that our new upper bound is going to be where our middle was. And now again, our upper bound is at 27. Our lower bound is at 18 still. And we're going to find the middle of that. So at this point, when we take the middle, we're going to be doing 18 plus 27 is 45. Divide that by 2, that's going to be 22.5. So we can either take 22 or 23. We'll just stick with 22. So 22 is going to be the index of our middle element. And now we have 68 there. Well, is that the element that we wanted? Yes, it is. So at this point, we can stop because we found the element that we want. So we return 22 to the user and we're done. Now, suppose we were to run into an instance where our lower bound somehow became greater than the upper bound. Well, at that point, that's when we know that we have to stop because the element that we're looking for is not actually in the list. So let's go ahead and implement this in Python. So we can start by creating our binary search function. We'll just call it binary search. So def binary search. And so we'll need two parameters. We need one which represents the element we're searching for. We'll call that element. And we'll need another that represents the list that we're searching in. And keep in mind that this has to be a sorted list. So we'll just call it LSG. Now inside our function, we have to first start off by defining what bounds we're going to use from the very beginning. So let's call them low and up. And let's set this equal to 0, comma, length of list. So we want to start the lower bound at 0, and we want to start the upper bound right at the end of the list. So up is not actually going to include the element that it represents. It's actually going to be an index 1 above the range it actually represents. And now we have to define our loop. So we're going to use a while loop here. And we're going to say while low is less than up. And that just basically means while we have a valid range. Because the moment that low becomes equal to or greater than up, we have recognized that we no longer have that element in our list. So we can just return nothing. So while low is less than up, now we have to define a mid variable. And that just represents the middle of the range that we've identified. So mid is equal to. So the way we identify the middle is we just take low plus up, and we can just floor divide 2. It's important to floor divide 2 because we're going to use mid as an index of list. And if we try to just regularly divide 2, that could produce a float, which could give us an error because we can only use integers for indices. So we're going to floor divide by 2. Now once we have mid, we can evaluate the element at that index and we can compare it to element. So first we want to check if element is the element at mid. So if element is equal to list bracket mid, then we have the element that we want, so we can return the index. And the index is going to be mid. Otherwise, there's two cases now. The element that we're looking for is going to be less than the element that we are currently on, or the element that we're looking for is going to be greater than the element that we're currently on. So let's account for the first one. So elif, the element that we're currently on, is less than list bracket mid. That means we have to modify our upper bound. We have to make that equal to the current mid. So up is equal to mid. And then our second case here, that can just be else. So else, we have to adjust the lower bound. So the lower bound is going to be mid plus 1, because we don't want to actually include the middle. And finally, if at any point we don't actually return in this function, if we break out of this loop without returning, we just want to return nothing because we haven't found the element in our list. So return none. And now we can test our code. So we have a list of numbers here, and these are all sorted. And these were the numbers that we were working with earlier. So now we want to print the index of 68. So I'll just say index of 68 and then comma, and then we're going to say binary search 68 in numbers. And that should be all we have to do here. So we can go to the terminal and test out our code. And we find that 22 was the index of 68. And that actually happened pretty quickly. Now suppose we wanted to do the same binary search on a very large list. Let's say I had a list of numbers. Let's call it sequence. And let's just say it contains 10 million numbers. So I for I in range 1, and then 10 to the power of 7 plus 1. So that's just 10 million numbers there. If we try to do a linear search, it's actually going to take quite a bit of time. So let's say I want to find item is equal to 9999995. Let's say that's the element that we're looking for. So we can perform a linear search here. So we can say I is equal to 0, and while sequence I is not equal to item, we just keep incrementing I plus equals 1. We can print found at index I. And that should be it for the linear search. So when we run this, let's just comment this line out. When we run this code here, we're going to see that it's taking a few seconds to actually find that element. Now let's do the same thing but with a binary search. So I still have my same sequence, but let's comment the rest of this out. So let's say I is equal to binary search, and we're looking for, so let's uncomment this actually, we're going to need it. Let's look for item in sequence. Now when we run this, it's going to be much quicker. So you can see that it was way quicker. It may not have looked like it was quicker simply because my machine is a little slow, but if we run it again, we can see that it found it very quickly. And if we indicate where we're starting, so print start now, keep in mind that when we're actually generating this list, this itself will take a bit of time to generate the list. But now when we run this program, we can see that almost instantaneously after we say start now, we're printing the index at which we found the element. Versus if we were to use our previous code, where we're doing a brute force linear search, notice that there's a few seconds in between start now and found at index. So this really identifies why it's important to use a binary search if you're going to search through a sorted list. And I hope this video was helpful.